Alrighty, so here we are back at it again with quantum mechanics, and this time we are learning about linear algebra. I was starting off with some of the basic bits for now, and of course, the reason why is because linear algebra can be a deep topic, probably as deep as calculus, and that means it takes some time of getting used to some of the things. Now it's different. So this time we're just going to focus on the start of linear algebra, and start with superposition. And you might remember it from last time, but we'll do it again. And then some linear independence, and then the inner product, or maybe sometimes called a dot product. You know, and maybe we'll do some cross product as well, but that'll be in a minute. Anyway, let's get into it. So, linear algebra. First, we better talk about that term. What does it mean? Well, you know, let's say that we have, an X, Y grid, you know, and on this grid, you can have a vector, like an arrow, like this. Well, what would happen? We'll call this vector V. But what happens if we have V times 2? Well, the answer is quite simple. We have another vector right on top. And if we have it times 3, we have another vector, and so on and so forth. And if we have a vector times, say, infinity, an infinite set of vectors, it will actually go on and form a line like that forever. It just goes on forever. And it might also go backwards forever, forming a line. Now let's say that we're doing operations on vectors, say adding v plus v, or v minus, or 2v minus v, then that is algebra. And obviously these terms together give us linear. That was goofy. Linear algebra comes from the study of vectors. And the reason why I call it that is because it's due with lines. But first, we have to talk about superposition. So imagine that we have, say, a baseball. Looks a tennis ball, but it doesn't matter. And let's say we have like a hand. I've never been that good at drawing hands. But anyway, as you throw the baseball, it has a vector, which we will call H for the hand vector. The vector from throwing it. It also has a little bit of drag, which we'll call the drag vector. By the way, I'll draw like an arrow on top to show it's a vector, because this is vector notation. And it might also have, say if there's a gust of wind, it might have a wind vector, which we would call W. And of course it has the gravity vector, which we will call G. And let's say that we wanted to show the sum motion. Where's the baseball actually going? But it would actually be an addition of these things, Basically, the, shall I call it, the baseball vector, where it's actually going, is equal to the hand vector plus the drag vector plus the wind vector plus the gravity vector. And this is what we call, linear combination is what is usually called. But blah, blah, blah. But we here, because we're doing with quantum mechanics, this is where that gets thrown around a lot. We will use the word superposition of this thing. Like the baseball vector is a superposition or a linear combination of all the vectors that are acting on it. And this is important. This will be important later on when we talk about vector transforms. But imagine a vector that we will define as being 3, 4. What does this mean? Well, this means you take 3 steps to the right and 4 steps up. So let's draw that. This 1, 2, 3, and another one. 1, 2, 3, 4. And as we add these all together, they will create our vector. So as you can see, the vector is a sum. It's a superposition of the 3 right vectors and the 4 up vectors, which is equal to the v vector. And this is true, say, on a grid. For example, if we have the xy grid, we have the y and x. And if we draw that vector again of, was it 3, 4? You might normally go like 1, 2, 3, and 1, 2, 3, 4, and you might try to draw something like this, but this is actually a combination of the 3 x direction vectors and the 4 y direction vectors. Say combination of the vectors. Now obviously we can do some vector operations, like if we have v, if that is equal to, say, 2, 7, and if we have another vector, we'll call it L, which is equal to, say, 3, 4, and we want to say have a third vector U, which is equal to L plus V. And then we just add these components together, which would be equal to 2 plus 3 is 5, and 7 plus 4 is 11. It's a superposition of L and V. And, there's not much to this. But, any vector is like a combination, or can be a combination of different vectors. Even, x vectors and y vectors, or z vectors, or, the heat vector, the velocity vector, and the momentum vector, and whatever, and this is where we get into our second topic of, I better write this, linear independence. So, as you might recall, we can sometimes add vectors together or add them to themselves to create different vectors. But sometimes it isn't possible. So suppose we have a vector v, which is equal to, let's say, 3. Let's go with something simpler. 1, 0. So it looks like this. I will have a vector t, which is equal to, let's say, -2, 0. The idea is that we can, let me think of the vector. That's not very good. 0, 1 vector. So it looks a little bit like this. Well, we can combine these using scalars. So if we have a vector u, it can be equal to, let's say, a times v plus b times t, where b, a, and b are some numbers that basically scale some of these vectors and make them bigger or smaller or whatever, you know. Um, but what if, we can't have that? Let's say t, can we create a combination using like a times v? Well, the answer would be no, because if you multiply any number, say like 4 times t, well, that's just going to equal 0, because anything times 0 is 0, and 4. And as you can see, we will never get to 1, 0 just through t alone. We can combine t to itself multiple times and we'll never get v. And the same way again, we can add v vectors together, but we'll never get to t. And so we say that v and t are linear. That is not very well spelled. Linearly independent. Because you can't combine v with itself to get t, and you can't combine t with itself to get v, but you can combine v and t to get a lot of other vectors. And so if we have some vector u, which might be, let's say it's like, I don't know, u is equal to 4, 8, well then it's not independent, because we can just set a equal to 4 and b equal to 8, and we'll get to u. And so u is not independent of v and t. And this will come up again later when we look at like quantum spin. But for now, that's all you have to think about at this moment. That's all it means by linearly independent. It means that you can't combine the vectors to get the other vectors in the set. Let me think. Now, before I go into dot product, I have to go over some notation. I've often been representing vectors as something like, let's think of a number like 2, 7. But often in the future, what we will see is they're represented as columns. V is equal to a column with 2 and 7. And this is called matrix notation. And it would become very relevant in the future. And as a side note, a row vector, we call it V transpose. Maybe I better spell that. Is just the vector more or less turned on its side. So we have 2, 7, instead of it being a column. Now, why is this important? Well, we're going to do something called the dot product. And, I'm going to show it to calculate. It's not that hard. Let's say we have like a vector, which is equal to 3, 2, and we want to take dot product. V dot V. Well, the way we do it is you take the vector transpose times the vector itself. So as you might recall, v represented as a column would be 2, 3, and vector transpose will be equal to 2, 3. And so v transpose times v is equal to this. You have the row vector 2 and 3, and the column, which is 2 and 3. And the way that we do this operation is we take the first variable, the first element in the transpose in this bit, and we multiply it to this bit. That's the first step. So take 2 times 2, and then next we take this element and move it into this element, and we add it. So it's going to be 3 times 3. So that's going to be 4 plus 9, which is equal to 13. That's the dot product. And if you might recall, this is a bit like Pythagorean's theorem with a squared plus b squared equals c squared. And it is, because it measures how much the vector is, how strong it is, so to speak. But it can also work with other vectors too that are like opposite to each other. Like if we have a vector of, say, 1, I'm going to go with 1. And, another vector L, which is equal to, let's say, 2, 3, then a V dot L is equal to V transpose times L, which is going to be 1, 1 times 2, 3, which is going equal, 1 times 2 plus, get out of here, and times 2 plus 1 times 3, which is going to be 5. And basically this measures how much they are in line with each other, because you can imagine vector v looking like this and vector L looking like this. It basically how much they are pointed in the same direction. For example, if they were at 90 degrees, like if vector L were to look a little bit like this, and vector v would look a little bit like this, so that we have right angles, then v dot L would just be equal to 0, because they're pointed the wrong ways. They're perpendicular. And this will be important later for like a vector version of the Heisenberg uncertainty. And so I'm going to go. That's technically all there is that I had planned for today. So we're going to go through a couple of examples to hopefully drill this in over what we learned. So let's say that we have a vector which is equal to, let's say, I don't know, 7, 7. Another vector L, which is equal to, let's say, 2, 2. And another vector A, now I'm not going to go with A, U, which is equal to, let's say, 10 and negative 3. Which one of these are linearly, or I guess not linearly independent? That's terrible writing. But as you can see, it would be V and L, because V would just be equal to some value, whatever it might happen to be, times L, because they even have the same numbers in both slots. So if like V is equal to this color and L is equal to this, it would look a little bit like this, where V points in this direction and L points in like that. And as you can see, the V is just a bigger version of L. And so it's not independent, because you can just stack more of the L vectors onto each other until you get to the V vector. But U would not be, if U is this color, for example, then it will look a little bit like that. And as you can see, it's not stacked on top of the other vectors, so it's independent of L and V. Let's take, say, a dot product example. Let's say that U is equal to, let's say, 7 and 10, and that let's go with the letter W is equal to 2 and 3. What would be the dot product, or the inner product, say U dot W? Well, that would just be U transpose times W, which in this case it would be 7, 10, and then 2, 3. And obviously, we can link these together, and we can link these together, so it becomes, let's say, 7 times 2 plus 10 times 3. I know this is 14, and this is 30. Oh. And thus the result would be 44. And well, this wasn't too dense. An example. Let's say that we have two more vectors. We'll call V will be equal to -1 and 1. And, U will be equal to 1, 1. That should do. And what would be V dot U? Well, it would be V transpose times U, which would be -1, 1. That's all these lines gonna look the same. And 1, 1. And if we were to say take these together, it would be -1 times 1. See this one here, this other one here. That'd be plus 1 times 1, which of course would be -1 plus 1, which would be equal to 0. And as you remember, 0 means that if the dot product is 0, then that means they are at right angles to each other. So like U looks a little bit like this, and V looks a little bit like that, and this here is a right angle, which means that U is completely separate from V in this scenario. It doesn't point at all in the same direction. And there's not much else to this. I will go more into how this applies into matrix quantum mechanics and vector mechanics later. But it's very helpful to get this down, because one of these days I'm going to go into like special relativity, and that also has a huge role with vectors in linear algebra. Anyway, I hope that wasn't too confusing. Anyway, they probably learned a lot. Learned about vectors and some notation, and you learned about dot product and uh, how we can see if the vectors are pointing in the same direction and if they are linearly independent and whatnot. And this might sound very abstract right now, but it will make a lot more sense next time. Or at least it's going to sound more useful. Anyway, see you another time.